Good day everyone. Today's topic is about hashing, rehashing, and how the collusion is avoided in the hashing technique. So we'll be seeing about what is hashing. We'll be then discussing about how hashing function is done. Then we'll see how collusion can be avoided and what are the techniques to avoid collusion. We are using separate chaining, and if collusion happens, how to resolve it. So that can be done using three techniques. One is two techniques. One is open addressing. In that we have to see three techniques, and then we'll be seeing about rehashing and extendable hashing. So first let us see what is hash table is. So hash table is another data structure which is in form of array format. So here the data value will be having a unique type of index for its accessing. So here in this data structure, the insertion and search will be performed very faster than the binary searching. So hash table will be using an array structure which is having a storage of medium size, and it will use an hash technique to generate an index for each element that is inserted into the hash table. So what is hashing? And hashing is a technique to convert a range of key values into range of index of an array. So we are going to use a modular operator to get the key value that are going to be inserted into the hash table. For example, if I have a table size of 20, then each element will be performed with the mod operation with 20 to find its location where it will be stored. So let us see an example. Now let us see, I have key 1, 2 and 3 which will be given to the hash function. Based on the value of the hash function, each element will be stored in the particular index in the hash table. So let us see an example for this. So now this is the example. So each number is given with their own hash values. Okay, so let us see how it is inserted in the hash table of size 20. So when 1 is given, 1 will be performed with the mod function of 20, so it will result in 1. So it will be stored in array index of 1. Similarly, when 2 is given, when 2 will be performed with the hash 20 of 2, so you will be resulting with the remainder 2, so it will be stored in the index 2. So similarly for each element 42, 4, 12, 14, 17, 3 and 37, where they have to be stored, their array index will be calculated using the hash function. So when you are doing this, they may create the same index for some items. For example, when you see here, I can have 17 mod of 20 is giving the index value 17, and 37 mod of 20 is also giving 17. So two items are about to be stored on the same location. So this will result into the loss of data or some collusion happens. So this collusion will be handled using a linear probing technique. Like a simplest technique, what we will be using is, we will try to store it in the next location. That is, when it creates the same index for two different items, we will try to find whether the next location is empty or not, and if it is available, then the element will be stored in the next location. And this technique or this approach is referred as a linear probing. So you can see here what happens is, when 17 is tried to be inserted, it will be stored in the index of 17. When 37 comes, it will be again stored in the index of 17, but 17 is already occupied, so it checks whether the next location is free or not. If it is free, then 18 will be stored in the next location. So let us see how the data item code is done. So you will be using a special data structure. So we'll have two values. One is the data item and another one is a key value. So when hash item is given to the key value will be performed with the size of the table, and it will return the array index for this. So what are the operations that will be performed on the hash table is, you can perform insertion, deletion and search. So how search operation will be performed? So first thing is, we have to compute the hash code for the given key. Okay, so usually you will be not giving given key, you will directly work with the element itself. So you will try to find the array index value for the given element, and with that element we'll try to go to that index and find the cell value. If the cell value is equal to the searching element, then it will print the element is found. Otherwise it checks the next element whether it is equivalent or not. Okay, so this is how a search operation will be carried out. So simple searching technique, we will be searching. So here you can see you will calculate the index value for the hash index value. Then you will check whether the hash index value is not equal to null. So if it has any element, then only I will go for the searching process. If it is equal to the key element, then I will print the element is found in this element. Else I will just increase the hash index and I will go to the next cell to check whether my element is found or not. Next we will see the insertion operation. So same thing, we will try to get the key value, calculate the hash index, and we will go to the hash index value. If the cell is empty, we will insert the element. If the cell is not empty, we will increase the hash index and we will go to the next cell for its insertion. So the coding is so similar. You can see when hash index is calculated, we will check whether it is not equal to null, means we will increment the hash index. Then finally, the hash index will be holding the item which is to be inserted. So the next operation is delete. The same thing will happen. We'll calculate the hash index. We'll go to the particular location. If the element is found, we will delete it. Otherwise, we will increment the hash index to find the deleting element. So you can see here, again, we will calculate the hash index. We'll put it in a while loop. We'll search for the hash index. When it is done, we'll try to delete it and reduce the hash index value one by one, and we'll try to do that. Okay. So next thing we are going to see about collusion avoidance. So when two elements are resulted to a same position in the hash table, we call it as a collusion. Okay. So we can avoid collusion by two ways. One, you can increase the so the number of collusion is mainly dependent on the number of inserts we are performing and the number of spaces available in the hash table. So if you are about to avoid a collusion, when there is a 50% of table is getting occupied, we will go for the rehashing technique. Okay. For example, if the table size tends to help the avoiding the collusion, means if there is only 5 elements, let me take the table size as 10, or I will take the table size as 60. When my table size is getting increased, it is been occupied with the inserting element, I will try to increase the size of the table. So usually you will take the table size as a prime numbers in order to avoid the collusion. So the collusion resolution is, so we are to the maximum extent we will try to avoid the collusion by increasing the table size, but the best option is to resolve the collusion. So when two elements are trying to get stored in the same location, we will try to relocate it. Okay, so here we generally use only the collusion resolution mechanisms. So we have two techniques. One is separate chaining and another one is open addressing. In separate chaining, we'll be using a adjacent linked list, and in open addressing, we'll use the three techniques here. So first we'll see separate chaining. So each array index will be holding, it will be stored in a array. So you will have array, initially all the arrays will be of same size. So here I am having a hash table of size 10 that holds the pointers to each linked list. So when you are trying to insert any element, we will give it to the hash function and we will get the hash index. Based on the hash index, there you will create a new node. For example, when 10 is inserted, so the element 10 is inserted, my table size is 10. So your hash function is element with the mod of table size. Okay, so when 10 is inserted, so 10 mod of 10 will be giving 0, so it will be stored in 0th location. So what happens is separate chaining, you will create a linked list from the 0th position. So next element is 22. So when you perform 22 mod of 10, it will be stored in the second location. You will have a separate link. So next thing is 86. So you have 86 here. So 86 mod of 10 will be giving 6. So 86 will be stored in 6th location. Now when I try to insert 12, so 12 mod of 10, which will be 2. So you can see already there is an element is connected to the second index. So what happens is the 12 will be inserted as a first element, that is it will be added as a first element before 22. So what happens is 22 and 12 will be done, that is we will be performing add begin operation with the linked list. So when 42 comes, what happens, 42 will be added as a next element. So you can see 42, 12 and 22 will be done. So this is the concept of separate chaining. So what will be the worst time for finding it? So if a single hash index is having 100 nodes connected to it, then that will be a similar to a linear search in the linked list. So the only thing is we will be having a bad luck is if your hash function is designed wrong or it is designed very badly with a bad concept, then it will result in a worst case for the separate chaining. So what will be the worth of avoiding this worst case scenarios? You will be using small size of buckets that will be connected to the each index. So you can have a balanced tree for the entire 10 index value in the hash table. So in this way we can avoid the worst case scenario in separate chaining. So what are the best thing we can do with the separate chaining is you can use linked list and array linked list implementation or array implementation for handling the separate chaining, or you can combine array and a linked list combination, which I have shown in the diagram for separate chaining. So each time when you try to resolve a collusion, you will try to insert the element at the beginning itself. So do not travel towards the end of the linked list to insert the element. So we will try to insert it in the beginning itself, so that will be very easier for us to improve the performance. And similarly, if the list will gain importance, if it is sorted, it will be more important, but the sorting will be more efficient if the number of element is very less. So next thing is what will be the basic load factor we'll be using here is, so the load factor for the separate chaining will be mostly dependent on the number of elements and the table size. So for example, if there are 5 elements out there, then the load factor will be of, for 10 location, it will be of 5 by 10, it will be of 0.5. So, but if you have more number of elements, so 1, 2, 3, 4. So if you have more number of things, the load factor will be increasing, which will affect your efficiency. So you can see I have inserted 21 elements with my hash table. So the load factor will be of about 2.1 over here. So in some cases, the average time taken for each bucket will be based on the load factor. So it will be of load factor for the each unsuccessful comparison, and for each comparative successful, it is mainly based on the load factor for the separate chaining. Okay. So let us see in deletion in the separate chaining, it is not too bad. So you have to find in the first, you have to find the hash index value. Then in that index value, you have to travel through the linked list to find the deleting element. Okay. So this is so similar to and sensitive to the underlying bucket structure, that is the linked list that is connected to the each and every index. So its complexity will be equivalent to the deletion of a node in the linked list. So next technique we'll be seeing about is open addressing. So open addressing is an example for resolving the collusion by trying the sequence of other positions in the table. For example, when there is a collusion, if the next location is free, the element will be stored in the next location. So that is the major concept of open addressing. So what is the drawback in using open addressing is, if the table size is too large and if majority of the table is being occupied, when a collusion happens, it has to travel through all the elements to find a vacant split. So that is a major drawback in the open addressing. So here the drawback mainly depends upon the load factor. Okay, so let us see an example. So let us see the hash function for the open addressing. So you can see this is the hash function. So this is the hash function we are using. So h of key will give the index value plus f of I. So here f of I is the number of collusion that is happening for the hash function. So initially it will be like a h index plus the number of collusion with the mode of table size. Okay, so with the mode of table size. So we'll see an example. So this is the open addressing. So we have 10 locations. So what is the difference between the open addressing and the separate chaining? So in the separate chaining, each and every index will be holding a linked list that is directly, or linked list of buckets that are directly connected to the particular index value. So the storing elements directly into the array cell is not possible in separate chaining. So here we are going to handle the collusion resolution using open addressing. So the first technique we are going to use is a linear probing technique. So let us see an example. So when my table is full, okay, so the 1, 2, 3 here in this value. So h key will be giving the index value, and 1, 2, 3 will be the number of collusions happened when we try to insert an element into the table. So let us see the first element, 38. Initially my table is empty, so there is no collusion. So you will have 38, h of 38. So what will be h of 38 is the simple hash function we'll be using here is mod function only. So we'll write like this, 38 mod of 10 plus the number of collusions. So it will be 8. So we don't have any collusion right now. So 8th position is empty. So 38 will be stored in the first position. So you can see 38 stored in first position. The next element is 19. You can see 19 is also not having any possible. So 19 will be stored in the format. So the next element is 8. So what happens is when 8 mod of 10 will be giving 8th position. So in the 8th position you have a collusion. So what happens is this h index, h of 8 plus 1, first collusion will be equal to 9. I check again 9th position, again a collusion happens. So it's happening with the second collusion. So you will be having 2. So which will be 8 plus 2 is 10. We don't have 10. So we will relocate it to mod of 10. So it will be going to 0th position. So 8 will be stored in 0th position. So the simple concept is we will check for the next location which is free. So when 8 is come, then next location it will go for 0th position and it will check the position whether it is available. So now if you see where 10 will be inserted. So the next element is 79. So 79 will be inserted. So what happens is again when 79 mod of 9, mod of 10, it will give 9. In the 9th position you have a collusion. So 9 plus first collusion will be 10. So it will go to 0th position. Again a collusion. So with the 0th position plus 1, plus 2, the same thing with the 9 plus 2 it is 11. So 11 mod of 10 will be first position, again a collusion. So 9 plus 3 it is 12. Again the table size 12, it is 10. So you will go for second location. So you will have, first location is still free. So 79 will be stored in first location. Okay. So this is how the mod calculation is done for linear probing. So when 10 comes, again 10 mod of 10 will be 0. So h of 10 is 0. So we have in the 0th position we have a collusion. So h of 10 plus first collusion is 1. So first position is also locked. So h of 10 plus second collusion is 2. So second position is free. So 10 will be stored in second position. Now what will be your load factor? So it is based on 5 elements are there, 10 locations. So it will be 0.5. Okay. So whether the load factor can be increased? No, it cannot be increased, and we will try to do that. So what are the other operations we can perform? So you can perform search and delete and insertion. We have seen the insertion. So we can perform search operation. So the same trial or same process will be carried out. We'll give it to the function. If there is a collusion, then the successive positions will be searched for my process. So when you go for deletion, it must be a lazy deletion, because when the first element, if the index value does not result the deleting element, then I have to travel through each location to find my element to be deleted. Okay, so this is what we call it as a thing. So where this open addressing will be mainly used is, it will be used in primary clustering process. So here it tends to produce a clustering process where to find a space where it can be accommodated. So the linear probing will be a very bad idea, because when there is a collision happens, it will just travel towards the next position for its processing. So when you analyze the linear probing, if you have with a very less number of elements, its performance will be too good. When you have a more number of elements in the table, then the performance of the linear probing will be a problem with that. The second technique we are going to see here is quadratic probing, which is an alternate for a linear probing. So here we'll be using the same function h of key plus f of I percentage of table size. Here this f of I will be of function I square. Okay, so for each time the collision happens, it will become into, just goes on with the process. First, when no collision happens, h key plus percentage of table size will give the h index. When there is a first collision, I square, so 1 square will be 1. For the second collision, it will be 2 square, it will be 4, and for the third one is 9, and it goes on. So it will goes up to I square, so that it will try to find the element. So here we will see an example how it works. Let us use the table size 10. Now I want to insert 89. So I just perform 89 over here. So 89, there is no collision. Okay, so mod of the table size 10, so it will be of 9. So next one is 18. So what is the 18 is? 18 will be of, again, no collision. So mod of 10, so you will have 8. Okay, so 18 will be stored in 8th position. So the next element is 49. So what happens is 49 will be first trying to insert with the 49 percentage 10. So collision happens. So you will have the h value of this. So the 49 plus 1 is, which is nothing but 9. Okay, so the value of this is 49. So which is h of 49. So which will be 9. So 9 plus first collision, what is 1 square, which will be given to 10. So it will be in 0. So we will be storing it in 49. Now let us see the insertion for 58. So what happens with 58 is, again a collision happens. Okay, so it tries to store it in 8 plus 1, 9th position. So h, this is h of 58, which will give 8. So 8 plus 1, 9. Again a collision happens. This is second collision. So h of 58, second collision to 2 square. So which will be equal to, h of 58 is 8. 8 plus 4 is 12. So 12 mod of 10 will be of 2. So whether 2 is free? Yes, free. So 58 will be stored in second position. Next is 71. You can see again a collision happens for the first time. For the second time, it is for 1. First collision, so it will go to 9 plus 1, 10. So again 0th position is occupied. Again a collision. So you'll have 9 plus 4, it is 13. So 13 divided by 10 is 3. So you'll be having here. So I will write it like this so that you will understand. So this is h of 79 plus 1 square. Okay, and this is h of 79 plus 2 square. So this will be equal to 9 plus 1, and this will be equal to 9 plus 4. So which will be equal to 13 divided by 10. Okay, so percentage mod operation will be performed. For next element, okay, so another quadratic example, we will see the same example with only table size of 6. When 76 will be stored in 6th position, 40 will be stored in 5th position. When 48 comes, What happens? 48 by 7, it is 6. Again, collision happens. We'll try to insert with the first collision value, so it will go to 0 position. Then when 5 is done, it will be stored in 5th position, so it will be a collision happening. So you will be so for 5 you will have a collision. So 5 will be 5 plus 1 square, which will be 6. Again, 6th position is also a collision. So 5 plus 2 square, which is 9. Okay, so greater than the table size, it will be equal to 2. So 55 will be stored in the second position. Now 55, same thing will happen. So 55 mod of 7 will be 6. So 6th position is occupied. So 6 plus 1 square will be 7, which is 7 mod of 7 will be 0. 0th position is also occupied. So 6 plus 4, that is 2 square, which will be 10% of 7, which will be 3. So it will be stored in third position. So you can see 55 is stored in third position. So here the quadratic probing and hash function is runs based on the table size. So can you can you guess where 47 will be stored? So 47% of 7 is 5. So 5 is occupied. So 5 plus 1 square, which will be 6. 6 is occupied. A collision happens. Then 5 plus 9, which is 9%, 7, which will be 2. Again, a collision happens. So 5 plus 9. Okay, sorry, one. Sorry, it is one sec. It is actually 4. 5 plus 4 is 9. Okay, then 5 plus 9 is, it's about 14%, 7, 0. So it's again a collision. Then 5 plus 16, it is around 21%, 7 is 0. Again, a collision happens. 5 plus 25 is 30. 30 by 7 is okay, what will be 30? 7 5 of 35. 5, it will be again 5, again collision. What happens is, you will not able to find an element for the position to be insertion with the process. So what happens is, it goes on and it will not be getting a place to be inserted into this. So this is the problem with your hash function. Okay, so you will you will be failing for all the cases. So the hash function needs to be processed properly. So you will choose the quadratic function f of I in such a way that it should be of a size, the table size should be of prime, and you should try to find your empty slot with the load factor which is less than half of the table. So when the table is filled with half of the element, we have to go for rehashing technique in order to avoid the space availability. We are not able to find the space for that. So next thing is, so we'll be seeing about double hashing technique. So what is double hashing technique is, we will use a separate function called g function for a hash function. So you can see here it is of I into some factorial function. So when you see an example for double hashing, your table size is going to be of 10. Your hash function is of a key. So h key is equal to key of the mod function, and your g key is 1 plus key divided by the table size mod of t minus 1. So let us see the example where happens. So 13, 28 will not have any issue. So because my table is free, so you can insert it. So 13 will be stored in third position and 28 will be stored in 8th position. When 33 comes, okay, now you have to find, it is going to be a collision. So you have to give it to g key. So when you are giving it to g key, so what happens is, it becomes 1 plus the g key of divided by 10, so which will be 3, and 3 mod of the table size 9 1. So this is a function, so we are trying to implement in this function. So when you try to insert 3 mod of 9, which is going to be of 3, so 1 plus 3 is equal to 4, so 33 will be stored in 4th position. Okay, so you can see 33 is stored in 3 more 9 is 4. Okay, Okay, I've done something wrong here. So 147. So 147 divided by 10 will be of 4. Okay, sorry. Okay, 14. So 14 mod of 9 is 1, 6. It's about 6. How it is going to be 6? 9. So 4 are 9. It's not 15. It's 6. Okay, 5. 5 plus 1 is 6. So you'll be giving it to 6. So H key, 1 second. Right, you'll just see here. So what is the difference here is, so we have calculated G key. So what is the function here is H of the key element plus I into G key. Okay, so I is the number of collusion. So here we have first collusion. So you will be having 1. So G key value is 4. And what is H key value is 3. So it will be equal to 7. So 33 will be stored in 7th position. Now when it comes to 147, so G key, you can see the formula for G key is 147 divided by, so 147 divided by 10. So remainder is given here. So 14 mod of 9, which will be 5. So 5 plus 1 is 6. So your H key of 147 is about 7 plus first collusion into G key. Okay, so we have 1 plus 6. So 7 plus 6 is 13. So which will be 13 greater than the table size. So again we will perform mod with 10. So you will be having third position. So 147 will be stored in third position. So this is the technique for double hashing. So next thing is 143. You can see the G key value is again the third position. H of 43 will be 3. So plus I into G of 43. So which will be 1 plus, what is G of 43? So 43 divided by 10 will be of 4. 4 mod of 9 is 4. So 4 plus 1 is 5. So you will have 5 over here. So which will be 8. Okay, so you have again a collusion happens here. Okay, so collusion happens. So we'll go for the next operation. So you will be having a next operation is 2. 2 into 10. So 3 plus 10 is 13. Okay. So you have 8 for a collusion. Then you can have 3 plus 2 into 5, which will be 10, 13. So 3, again 3 is also having a collusion. So 3 plus 5, which is 18. Again 8 is a collusion. Again 3 plus 4 into 5, which is 20, 23. Again collusion. You can see the same happen. What has happened for quadratic probing, again the same happens for here. So it is purely based on how you define your hash function. So again and again it will repeatedly storing over here alone. So again double hashing is also not safe because we may enter into a looping structure. So this can happen at least once when you are trying to store the elements in the prime locations. You have to change your hash function accordingly. So let us do a summarization. So what are the collusion resolutions we have done? So we used separate chaining, which is very easy to implement, but the load factor is a major issue in the separate chaining. So second thing is open addressing. We had a very easier mechanism for linear probing, but there are some overheads are there. We will be entering into an infinite loop in order to find a location for particular element. So we have seen an example with quadratic probing and double hashing technique. So to avoid this, we will be going for rehashing process. So what is rehashing process is, if the hash table is too full, then we have to create a bigger table and copy everything into the bigger table. So this will be very helpful to shrink a table, because it is very less helpful than shrinking a table, because when my hash table is filled 50%, there is more possibility of collusion. So to avoid collusion, we will consider the load factor. If the load factor is above 0.5, we will try to go for increasing the table size. So what would we do is, we will try to make the table size twice. If my hash table is 10, I will make my hash table into 20, or I will expect whether my table to be in the size of prime numbers. So this is getting twice the size will be guaranteeing about avoiding the collusion. Okay, So the more probability is about nearly 20 to 30% of collusion can be avoided when we are doing rehashing technique. So when the table size is increased, can we copy the same elements or the same elements which are already in the previous tables? The same index can be used for the new table? No, it is not possible. If you have done your hash function with the table size of 10, that values cannot be used for the table size of 20. So you have to rehash each and every element again to store it in the rehashed table. Okay, so that will be the issue over here. So the major thing is your space and time complexity will be compared with the rehashing function, and the table of size will be increased on a constant factor. So rehashing is called a closed hashing technique, because when my table is getting filled, I will increase my table size to double, and I will try to insert all the elements again into the new table. So it is a very expensive operation, because the rehashing will be using all the elements to be rehashed again into the new table. So it will be taking the complexity of O of n. So, and when do we do rehashing? Whenever my table is filled up to 50%, I will do my rehashing process. Or else, when there is a when an insertion fails in the rehashing, then I will go for a rehashing process. So let us see an example. So I have inserted 13, 15, 24, 16 into the table with the simplest hashing function with the mod of size. So this all the 4 elements are inserted. Now you can see nearly about 70% of my table is filled. So if I try to insert 23, it will become 70% full for my table. So now I need to create a new table. So I will take my table size is 70. So it's the next prime number we have after 7. Okay, so which is twice large as the old table size. So what happens is each and every element again will be rehashed. Now you can see 13 mod of 17 is 13 itself, so it will be stored in 13th location. 15 is again mod of 17 is of the same location, so you will be having 15 over here. So it is of 15. So 24 mod of 17 will be of location 8, so you will be having it in 8th location. And 13 we are already done, so next element is 6, so 6 will be in 6th position, and 23 will be in 7th position. So this is how the rehashing will be done. So we will be not using the same index value when the table size is increased. So the table size can be increased like as you like. So here initially my prime number is 7, the next prime number I can have is about 11 and 13, but it is not twice as the size of the table. So 17 will be twice as the size, so it is greater than 14. So the next prime number greater than 14 is 17, so I have taken 17 for my table. Once the table size is increased, each and every element will be rehashed again with the new table size. Okay, that's the most important point in the rehashing. So next thing is, there is another way of doing hashing is extendable hashing. That is, we are doing it as a external sorting. Like external sorting, we will be doing the rehashing with the extendable hashing. So here we'll be using a tree-like structure, and each block will be holding a set of elements in it. So consider a key that consists of 6 bits of integers. So you'll be using 6-bit integers, and the root can contain 4 pointers that will be holding with the first 2 bits of the each number. For example, if it is 2, so you'll be taking 0, 0, 0, 0, it is 1, 0. Okay, so this is the 1. So here, this is the number. Each and every number is a 6-bit integer. 6-bit integer number is being used, and you will be having an index for the first 2 bits alone. So you will be having 4 locations that will be having first 2 bits. Okay, so if you are having this index is based on the number of elements that are present. For example, if we take this, so I have 1, 2, 3, 4, 5, 6, and 10 and 12. I have more than 12 keys elements. So here elements are stored here, and this is the extendable index that we are using in extendable hashing. So this is an root index. So root index will be divided in the terms of 2 power 0, 2 power 1, and 2 power 2. It goes on like that. So now it is 2 power 2 index. So that means the first two bits, it is speaking, the popper will be taking about the number of bits from the integer. So which are the numbers that are starting with 00, that will be pushed into this bucket, and which are starting with 01, that will be pushed into the second bucket, and 10s will be pushed into third bucket, right? So now suppose I want to insert 100 so each element can hold 2 to power 2 elements only. Now if you see 10, already its bucket is having 4 elements. Now I have to increase the size of the bucket, but the size of the bucket can't be increased. So what I do is I will increase my index. So how do I increase this? I will increase it from 2 power 3. For example, now I will consider the first 3 bits. So you will be having 000, 001, 01. So now each and every element will be rehashed. Now this 000 will be in 001, 001 will be in 001 buckets, and this will be in 010 bucket. This will be in 110 bucket. You can see here it is in 110, and 11 the new element that is inserted is here. And these 3 elements will be in 101 bucket. So you can see these 3 elements are in 101, and the last bucket remains unchanged. So you will be having in the unchanged. So now if I try to insert 000, so that is I need to store 000. So you can see these 2 buckets are having a same, will be sharing the same bucket until there is a space is required. When this element comes, what happens is this bucket will be getting splitted into 2 boxes. So this will be similar to your B tree operations that we perform. So what happens is 000 and 001 will have a separate buckets. Now it will be getting done. So what will be the advantage? So it provides a quick access for insertion and searching operation when you are working with a large database. And the disadvantage is the algorithm does not work if you have duplicate values. So that's the problem with extendable hashing technique. So that's all about hashing and its techniques and rehashing. Thank you. I'll meet you in a new topic in the next session.